Hi everyone. Okay, this video is going to be talking about the standard normal distribution. Particularly it's PDF, it's CDF, how to deal with finding probabilities, some empirical rules, and then moving into other normal distributions that are not standard, but we can maybe standardize them. Anyway, we can discuss. So first of all, let's talk about what a normal distribution is. Now, sometimes it's not referred to as a normal distribution. It might be referred to as a Gaussian distribution, okay? Or maybe you hear of the bell curve before. Now, this is supposed to model a bell curve, okay? What that means is that if you had we can call it a Z versus 5Z axis. Okay, and I'll talk about the phi means in a moment. But it's a bell curve because it looks like a bell. Okay, this is your bell curve. Okay, well, a standard normal distribution models probabilities, okay, that follow this little bell curve. Now, there are many things in this world which can be modeled using normal distributions, okay? Things like marks in an exam, things like, we could say number of car accidents in a year, by age or something, okay? Whatever. There's a lot of things which naturally fall into this pattern, okay? Now, what does this pattern represent? Well, we normally refer to this axis here, the y-axis, or at this x value, or z value, that as the mean / median, okay? And what it's saying is that most people, i.e. the probability is, most of the people lie within close to the mean, which is the probability of landing close to the mean is quite high. So think about it as marks in an exam. When let's say it's a maths exam and the mean is a 70, most people are going to get around the 70, okay? Now you're going to have a few geniuses, okay, who do really, really well and get the 99s and the 100s and the 98s. Then you're going to have a few inverse geniuses who do much, much worse than the 70, okay? But it doesn't make sense to say, oh, actually, no, that's not the case. An exam has this sort of curve, right? Like you could say like the reciprocal, not even the reciprocal, like the reflection of the bell curve, okay? That means that very little people got near the mean, but a lot of people did really well and a lot of people did really bad. That doesn't sound consistent with how, the marks in an exam behave, okay? So usually they form bell curves. That is, they are modal, so single modal, and they're kind of symmetrical. Maybe not exactly symmetrical, but we like the idea of saying that most people lie within the mean or close to the mean, okay? And little people on either bounds. Perfect. Now, just like with every continuous distribution, we have to have its PDF. Now, its PDF is given by, I'm going to kind of draw that carefully, phi of z, okay? And I'll tell you why we're using z's. We use z's because we here have a standard normal distribution. And a standard normal distribution, as something we'll discuss in a moment, is a normal distribution that has a mean of 0 and it goes to negative infinity and positive infinity, symmetrical about that z equals 0 point. You might have other normal distributions which are shifted and dilated. And in that case, they won't be standard and we don't have to use z. But we just like the idea of conventionally using the z to represent a standardized normal distribution, okay? So instead of x values for whatever your probability is, we just use z. Anyway, what you can see here is this phi. I've kind of drawn it like this to highlight that that phi is lowercase phi, okay? And you can see here, this is e to the minus z squared over the square root of 2 pi. Perfect, 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 perfect. Okay, what are some things that we have, or what are some properties of the standard normal distribution? So the properties of Z, we could say capital Z, which is a normal distribution. Okay, or sometimes you might see it written as Z with a swiggle is given by N and then 0, 1. Okay, what does the 0 and the 1 represent? This 0 represents the mean, and this here represents the variance. Okay, so what this tells us, so the properties of our standard normal distribution, first, it's symmetrical about the mean, of which is Z equals 0. Perfect. Okay. What else do we know about Z equals 0? If we look back at our graph for this normal distribution, think about any continuous distribution function, right? Any PDF. When you graph your PDF, the highest point is considered your mode. Okay. So not only is Z equals 0 our mean, Z equals 0 is the mode. So that's the most occurring score. Now, if something is symmetrical at a particular point, doesn't that also make it our median? I mean, yeah, right? It's the middle score, means it looks exactly the same on the left, this is left for you guys, as it does on the right. And therefore, it has to be, I'm still recording. Yeah, okay, 666. So it has to be the median as well. Wonderful. So not only is Z equals 0 the mode and the mean, it's the median. Perfect. Okay. And what we know is, we know that in a, and I've kind of mentioned this already, that the variance of Z equals 1, and the standard deviation, so we can just say sigma of Z equals 1 as well. So just the square root of 1. This is important, and we're going to talk about this a bit later on. Okay. Well, now let's talk about, so we've talked about the PDF. Let's talk about the CDF, which is the cumulative distribution function. Now we know the cumulative distribution function for any continuous distribution is given by capital F of X as the integral from whatever the starting value of our function is, of where our function is defined for, to x of f of x t dt. Okay, so what does this t and dt mean? I know it might sound weird to have this t out of nowhere, but it's just used as a dummy variable. Okay, you would have already seen this when we discussed just general continuous distribution functions, or the PDFs, and then integrating to get CDFs for those continuous ones. Nevertheless, we can now model this thing for our standard normal distribution, or kind of just reflective for that idea. Well, our cumulative should look like this. It's because here we didn't use f, we used phi. That was lowercase phi. This here has to be uppercase phi. Now, uppercase phi just looks like a bit of a, like a this. Now it says capital phi of z, okay, is equal to the integral from negative infinity to z of lowercase phi of t dt. Okay. Again, that just means that we're integrating from the leftist bound, the most left bound. Now, as you can see on a PDF like this, we're going all the way to negative infinity and positive infinity. So we're going from negative infinity, integrating to a particular z. Okay. And if we just go back and write in what this would have been, it would have been e to the minus a half of t squared over, and what is this? See, I don't even know what this is. Square root of 2 pi. Sort of irrelevant, but whatever. And then dt. Anyway, instead of x's, you just put t's and dt's because I guess so that you don't integrate with respect to z and then sub in a z into something that already is in terms of z. It doesn't make as much sense as to just write another variable in and then sub in the z's afterwards. Okay, what does this look like on a graph? I mean, in terms of this cumulative? Well, if you have this same diagram as before, so let me just copy this thingy in, paste. If we have this thing here, then what does phi of z look like? Well, phi of z looks like, if I shade in blue, all the way from negative infinity up to some particular x value. So maybe I should have drawn in the line before I started doing this, but let's try and make that variable this, and we're going to call this point here the z. Okay, what it's saying is if you integrate from minus infinity all the way up to z, that's our cumulative. Perfect. Okay, now remember this is z as like the units, but this is z as in that particular z score. Okay, wonderful. Now, the question is, can we find the CDF? Can we actually integrate this thing here? 3-unit students, you may say, well, I can't divide by the derivative of my power because I'm dividing by, what is that going to be, negative t? Not possible. I cannot introduce new t's. And then 4-unit students might say, I can do this thing called integration by parts. Maybe if I let this thing here, I can take the 1 over root 2 pi outside and then say, let this be the u and then differentiate that and then let a 1 be the v dash and then integrate that and then do integration by parts. It could work. I'll ask you to test yourself and you realize that it doesn't actually work. Unfortunately, there are, extended proofs you can even Google online, which involve double integrals. And that's something that I didn't do to university. So we're going to just ignore that. So if this is supposed to be super useful and it shows up everywhere, what's the point of it if we cannot even integrate it? Well, the point is we actually have these empirical rules, okay? These empirical rules already exist for our standard normal distribution, which helps save us some time, and they are given on your reference sheet, okay? So let me just copy these in so I don't have to redraw this ugly diagram. They are given on your reference sheet, but sometimes you got to sort of derive it yourself, like particular percentages, but you'll see it's not too bad. So let's just paste here. So here we have the empirical rules for the standard normal distribution. You can see we know that the mean is 0 and the standard deviation equals 1. Wonderful. Well, the rules that you're given on your reference sheet are the following here. 68% lie between z equals -1 and z equals 1. 95% lie between z equals -2 and z equals 2. And 99.7% lie between z equals -3 and z equals 3. Let's just rewrite this a bit nicer. And z equals 3. Okay, what does that mean? Well, in our standard normal distribution, the standard deviation is 1. So the empirical rule from people who have integrated and already evaluated these percentages, okay, tell us that if you lie within 1 standard deviation of the mean, why is it 1 standard deviation of the mean? Because the mean is 0 and you're moving to 1 and to -1. That represents within 1 standard deviation, because the standard deviation is 1. You're saying that 68% of the scores lie between those two values. Okay. Now, that means from -1 all the way to 1, this area here should equal 68%. The next rule says 95% of scores lie between -2 and 2. That means 95% of scores lie between 2 standard deviations of the mean. So the mean is obviously 0, then you're between 2 and 2. And that means this whole area here should represent 95%. The last one, 99.7% lie between -3 and z equals 3. That just says that 99.7% lie within 3 standard deviations of the mean. Okay, it's pretty cool. It's actually pretty cool because you can then imagine like you're a teacher, right? And you're trying to talk about how your students did in an exam. And let's say you can somehow find out that your students follow a normal distribution. Percentages like this is a good way to be able to report to, the coordinator or the principal or whoever cares about saying like, you know what, 95% of my students got between 2 standard deviations of the mean. If the standard deviation was really small, that means your class is pretty consistent, depending on, they're pretty consistent. And then depending on where your mean is, they might be consistently good or consistently very bad. But it's very good to report on these sorts of things. Now, what are these numbers I've put in here? Okay. These are the numbers which are often going to be relevant in your questions that you might get in an exam. Yes, you're given 68% lie between -1 and 1. But because I know this is a symmetrical graph, I can then split up that 68% into 34 and 34. So I can potentially find the number of, or the percentage, or the proportion of whatever outcomes just between 0 and 1. Okay. And I feel like that one makes sense. But what about this 13.5%? Well, a good way of thinking about it is I know between -2 and 2, that's 95%. And between -1 and 1, that's 68%. So it means that just this area here and this area here, even though they should look symmetrical, but they don't, should be equal, and should just equal the difference between the 95% and the 68%, of which that is 27. Okay. And if you divide 27 by 2, you get 13.5 and 13.5. Wonderful. I think you can see where I'm going with the last one as well. Because this is 99.7, okay, and this is 95, that means 4.7% should be in this area and in this area. If you divide 4.7 by 2, that's 2.35, which is why I got the 2.35 here, 2.35%. And if you want to find the outer points, or this outer sort of bounds, the ones which are greater than 3 standard deviations from the mean, or less than 3 standard deviations below the mean, then you can say, well, the entire area under a PDF should equal 1. Okay. And if it should equal 1, and this is 99.7%, that means this thingy here plus this thingy here should equal 100% minus 99.7%, which is 0.3%. And then divide that by 2, you get 0.15%. Okay. This is very useful, and I want you to be able to get to these sorts of percentages quickly in your exam. Even when I do these questions now, I actually know that's a lie. I don't actually do this, but because I just know them. But I got to this point where I know all of my percentages because every time I did an exam before, I would draw out a little normal distribution and I would shade in the area which I thought was required. Okay. And I will do that in some of these questions. Perfect. So let's say I asked for a normal distribution okay, find. And then I'll say the probability, so this one we'll do together, the probability that capital Z is less than or equal to 2. Okay. Obviously, doesn't this correspond with the CDF evaluated at 2? Wonderful. Now you need to find this percentage. I don't want you looking back, maybe having screenshotted this image here and dealing with this because you're not going to get that. I want you purely looking at these, which are given on your reference sheet. Okay, so have that open or screenshot this. So then we come to here. You want to find the percentage of scores which are less than or equal to 2. So you're going to first draw out a normal distribution. Okay, they should be, approaching 0 and like that, asymptotic. This one kind of goes back up. That's not good. But anyway, and we want 2, and we want everything to the left, don't we? Because we're taking the CDF. Perfect. So how can we find the percentage which corresponds to this shaded region? It's quite easy, actually. If you put in what you know. Now, don't spam it with everything because a lot of it is irrelevant, but just put in -2 and say, well, what's the percentage between -2 and 2? The percentage that lies here is 95%. Now, that means how much must lie in this little region and this little region here? Well, it should be 100%. So the full curve minus the 95%, which is 5%, and then divided by 2. That means that's 2.5, and that's 2.5. So there's actually 2 ways. You can either say it's equal to 95% plus 2.5%. And where did I get that? I got that from this 95% plus this 2.5%. Or you can say the total, which is 100%, full thing, just take away this. So minus the 2.5%. Either way, you get 97.5%. Okay. Now I want you to calculate this next one for me, please. Using a similar sort of diagram. Okay, it's definitely going to be harder because I'm not going to make life super easy. It's the probability that Z is less than or equal to -1. Okay, maybe this isn't that hard. Anyway, have a go and pause and then unpause once you feel like once you're done. All right, unpause. Now, this of course can be rewritten as 5 minus 1. That's relevant, but I just thought I'd add that in there. Again, normal distribution. Doesn't matter how many times I draw these curves. Wait. Oh, why is this frozen? Okay, there we go. Oh, thank God. All right, doesn't matter how many times I draw these curves, always looks scuffed. I think I'll end up maybe getting one good one all of this entire recording. Anyway, of course, we want to find, if that's -1, we want to find this region here. Okay, so to the left of the -1. Well, it might be worth putting in the 1 and saying how much lies between -1 and 1. Well, how much lies here is just 68%. Okay, well, if that's 68%, then what must lie on either end? Well, it seems like whatever's going to lie on the ends is just 100%. So we can call this and this together should be 100% minus 68%, which is obviously 32%. And then if you want to find just part of it, you'd obviously divide that by 2. And then you'd say, oh, wow, this thing here is just 16%. And then this just equals 16%. Sick. I'm going to give you a few and I just want you to figure these out. Obviously, they're going to be a bit harder now because, yeah. So probability Z less than or equal to. That's actually quite easy. Let's just skip this and make this probability. And then I want you to also do. No. Alrighty, pause, have a go, then unpause when you're ready because I'm about to go through them. Wonderful. These ones look a bit different because, of course, now you have different numbers involved, right? Multiple instead of just being involved with one number on our diagram. So Let's draw in a normal distribution. We're looking between 3 and -1. That's the area which we're trying to find, aren't we? It's the probability that we lie between those two z-scores. Wonderful. Well, what I'm thinking we can do is we can say, well, what if I know this and I know this and I can do 100% minus those two? That's one way. And you could do it in other ways, but that's, I think, the way that's going to be the easiest. So let's just put in the 1 here. How much lies between 1 and -1? 68%. Now, if that's 68%, I think we just did it in the question before, but that means that this thing here and this thing here should each be 16%. Okay, so now we know that this thing is 16%. Now, between -3 and 3, what's the rule? How much do we know lies between -3 and 3? 99.7. Well, if that's 99.7, then we got to do 100 minus that. That's going to give us this thingy and this thingy. Okay. And that's 0.3. Then you got to divide it by 2 to get each side. That's going to be 0.15%. So in total, we have 100% minus the 16%, which comes from all of this. I know I put in the -3, but ignore that. That's not really blocking it off to just there. Okay, it's the entire thing. I just put it in there to help us with this side. And then minus the 0.15%. Now let's try and do this. Minus 16.15, so 83.85%. Yeah, that should be good. Okay, next one, probability z is greater than 2. Bit of a normal distribution. 2, -2. How much lies between 2 and -2? 95%. Now we want z is greater than 2, so we want this thingy. Perfect. Now, if we want that, we're going to say, well, how much must lie on either end? That's 95%. This should be 2.5, and this thing here should be 2.5. So this is 2.5%. Probably z is less than or equal to 0. I might say, is this so easy that it's a bit of a, but why does this seem so easy? Is it a bit of a trick? No, it's no trick. Because the normal distribution is symmetrical, or at least it should look like it, unlike that final, this drawing of mine. And we know that this is the median. Okay, this is the median. Then doesn't that mean that 50% of the scores are there? So if we're looking for z being less than or equal to 50%, less than or equal to 0, that just means 50% of the scores. Now, what do we know about continuous distributions? Continuous distributions are basically have exact probabilities equal to 0. It's really just about areas to find regions underneath curves, not to find probabilities of exact values. So exact values just equals 0. So therefore, it doesn't make a difference that it's less than or equal to 0 versus just less than 0. No, it shouldn't. It's still just going to be 50%. Perfect. Now, let's talk about the properties of the CDF. I'm surprised I haven't been making that many mistakes with CDF and PDF and all of that. Okay. So properties of the CDF. Why does it say? Yes. Now, of course, we know that what 5z is defined as, it's the area from the very left all the way up to a particular z value. Our first property is if you take 5 negative z this actually equals 1 minus phi of z. This might make life easy, particularly in the future when we have some scores or whatever. Okay. So this is one important property. Now, why does this make sense? Well, let's see. If I have a normal distribution, why does my right side look so good and my left side looks so abysmal? Okay, oh, whatever. 5 negative z means if you have some negative z value there, then you're trying to find this area here. Okay. Well, they're saying that it's actually the same as taking 1 minus phi of z. Well, phi of z is going to be from here, which is just the positive version of that number. Okay. But the area all the way to the left. So it's actually almost like you're finding, I don't know, maybe you should put it in a different color. Okay. That's what this is. So why is 5 minus z equal to 1 minus 5z? Well, if 5z is this, isn't 1 minus it just simply equal to this thing here? It's just whatever's remaining, isn't it? But because we have symmetry, this green region actually corresponds with this blue region here. Okay, and that's why we have this little identity. It's saying, instead of taking 5 negative z, you can just say 1 minus 5z, because this is kind of like the complement anyway. Okay, perfect. Now you might also get something written like this. And I think we already did an example of one here, the -1 and the 3. Okay, but you can see with this one, probability that, let's say, z is between two values, z2, z1. Okay, I'm not going to give any particular values for this. We can actually say this is capital phi of z2 minus capital phi of z1. Okay, perfect. Why does this make sense? Because if we draw out another normal distribution, which I feel like is becoming quite redundant now, particularly because I can't draw them well. If you have some z1 and z2, it doesn't matter whether they're both positive, whether they're both negative, doesn't matter. Let's just put this as z1 and put this here as z2. Okay. If you want to find the probability that the random variable takes values between z1 and z2, it means you're trying to find this region here. Okay. Well, what does phi of z2 represent? Phi of z2 is the sum from the very left up to z2. Now, if I'm just trying to find the blue shaded region, it seems like if I subtract z1, which I'll just put in green, then I'm left with particularly this region here. Okay, so that's where this comes from. Wonderful. So this here is obviously, it's in green, and the other one was the one in pink. Perfect. This property is very important, actually. They're going to come up all the time, particularly in the next thing we're going to discuss. Now, another point that I just wish to make. The probability that z is less than or equal to 0.5 does not equal 50% plus and then 34% over 2. Okay, probably like, where are these numbers even coming from? Well, a lot of times people make the mistake, especially early on, that if you're asked to find the probability that z is less than 0.5, you would draw out your normal distribution. And say, oh, this is actually so bad. No, I mean, what I should do is just draw one good one and just paste that in every single time. I feel like that does the job. I'm gonna copy this. Okay, is to say, well, if this is my 0, and this is my 1, and this is my -1, what it's asking me is I should take the area from 0.5 or from negative infinity all the way up to 0.5. Yeah. So if it's shaded, it will look like all of this. Okay. Well, we know already that this thing here from the negative infinity all the way up to 0 represents 50%. So that's where this 50% comes from because it's the median. So that's already 50%. But you might say, I know between -1 and 1 is 68%. That means between 0 and 1, it should be half of that, 34%. Let me say that's 34%. Well, if I just want this region here, shouldn't I say 34% divided by 2? Because it's just between 0 and a half, not 0 and 1. So I should just divide it by 2. The answer is no. The reason why no is because probabilities mean areas underneath curves. If you tell me this area here, which we call A1, is equal to this A2, then if they're the same area, then you can just divide it by 2. But clearly, A1 is greater than A2. And because of that, that means this region here should actually correspond to more than 16%. We don't really know what it is. We can't use our empirical rules to work for other numbers which don't line up with the -1, -2, -3, or 1, 2, and 3. Okay, so you're not allowed to do this. You know, that we can say here, I guess the region is not cannot be evenly split because that assumes that it's a constant curve or the areas are equal, but clearly A1 is greater than A2. Okay, so those are just some of our important properties. Now, you might say to me, well, how are we supposed to deal? Well, now you might say to me, how are we supposed to deal with cases where we do have z's being less than or equal to numbers like 0.5, okay, or 1.36? Okay, we can't use our empirical rules because our empirical rules are only for -3, -2, -1, 0, 1, 2, and 3. Okay, what about 4, 5, or 6 standard deviations, or anywhere in between? Okay, this is where we have to instead use something called a z-score table. Z-score table. So let's just write here, z-score table. Now, what a z-score table is a table that is provided to you, okay, that has basically the cumulative values, or the cumulative distribution functions evaluated at many, many z values. Okay, it's actually pretty sick. Now, where does this come from? Well, there's a bunch of nerds who study stats, definitely not me, who can evaluate these numbers. And here's an example of a z-score table. Okay, for example, what does this number here? Whoa, that's not what I want to do. What does this number here represent? Well, that number represents, see, this is like the you know, the tenths, and then this is the hundredths. digits. Okay, so that blue number there represents phi of 1 point. Well, I can't even read this. 1.05. Okay, which means the probability that Z is less than 1.05. Okay. Yeah, definitely not easy to calculate, is it? There's no empirical rule, but you get given these Z-score tables and you can end up finding out your cumulative straight from here. Isn't that kind of sick? I think it's pretty sick. And you can actually see some of your cumulative distribution value, like some of your empirical rules already here. First of all, we know that phi of 0 is 0.5. Why is that the case? Because phi of 0 equals probability that Z is less than or equal to 0. And we know that because Z is equals 0 is the median, that's 50%. Okay. What about for 1? 0.84134. Okay, that's like phi of 1. You might say, why is that so different to us? This is just because this is a more accurate example. Whereas here, I think we did the probability that Z is less than 1 somewhere. Maybe we didn't. Okay, whatever. It is what it is. You get the idea. You can go and you can correspond with these empirical rules from this table here. Now you can find one online. It's not a big deal. Or because I'm going to give you some questions, you can just screenshot this and then have it open as we go through it. But I'm not going to go through anything beyond what is given in the table. Okay, perfect. So this table can be used for a lot of things. Okay. Now I just want you to evaluate some of the following, please. So the probability that Z is less than 3.2. When you evaluate phi of 1.16. When you evaluate phi of 2.13. And then last one, I want you to evaluate probability that Z is less than 0.01. Okay, have a go. And once you're finished, just unpause the recording. Okay, you can see now once you've unpaused, those are my answers. Are they that hard? No, you just have to just look at the, look at the table. Okay, perfect. But what you notice is all of these Z values here are positive. Okay, what if I wanted to find something like this? What if I wanted to find the probability that Z is less than or equal to -3? We went to -3, we did -3.54. Okay, this is phi of -3.54. Obviously, there's no negatives here, and you're not allowed to just go and ignore the negative and find what 3.54 is. Okay, you have to actually do some other operation. Okay, so what's the other operation? Well, we already wrote about one of the properties, didn't we? I think the property was that if you have phi of some negative number, it equals 1 minus phi of the positive number. Easy. So now you just go and say 1 minus, and then you find out what phi of 3.54 is. Okay, so we're going to go back up to here and say 3.54, 3.54, 0.99980. So 0.99980. Okay. And by putting this into the calculator, we get 1 minus 0.99980 as, we can write this as 0.02%. Wonderful. Or you can leave it as decimal, doesn't really matter. Perfect. So really, we have to utilize those properties which I've written beforehand to be able to calculate probabilities where you have, to be able to calculate these sorts of regions, which might have negative Z scores. Okay, perfect. What about if I gave you, when you sort of utilize those properties to evaluate the following? So phi of 1.5, about the probability that Z is greater than or equal to okay, I'll just give you 5. So I'll give you these 4 and okay, I'm trying to give you some of the same ones just so that you can save some time. And then the last one, probability between 3. Okay, have a go, and yeah, we can evaluate. So, assuming that you've had a go, what we can just use is our properties. Okay, we know phi of negative 1.5 is going to equal 1 minus phi of the 1.5. These should all be capital Phi's. My bad. And then I'm not going to find out what phi of 1.5 is. You can just look at the table and then put it in. I guess that's kind of easy. But I want to focus on the properties part, or like being able to break it apart. Okay, this next one. I want you to draw a bit of a normal distribution. You're saying you want probability that Z is greater than or equal to minus 1.2, which means you're trying to find this region here. Okay, well, if you took phi of minus 1.2, you'd be getting this region here, right? Because it's the cumulative from the very left all the way to a particular Z value. So clearly, if you want to find probability that Z is greater than or equal to minus 1.2, you should take 1 minus 5 minus 1.2. Okay, I think that makes sense. Because it's just everything that's not including this. Now, what do we know phi of a negative is? Well, phi of a negative is 1 minus phi of the positive. So just expanding this out, we get phi of 1.2, which you can put into your calculator. So do you see how I'm sort of using these properties to be able to clean it up and find it in terms of positive Z values? Yeah, I hope that you answered yes to that. But now you see, so the probability that Z is greater than or equal to minus 1.2 is actually the same as the probability of Z being less than or equal to 1.2. So it's saying this region here, which we've tried to find, is actually the same as if I put a 1.2 here and as if I tried to find this area. Now, I think from the graph, that kind of makes sense. Because we know that this area equals this area, by saying, oh, I want the entire curve except for this, which gives you the blue region, that's kind of the same as saying, I want the entire curve except for this little part, which is what you would do if you wanted phi of 1.2. But anyway, you can see, and then you just find phi of 1.2 in the table. You can see in the same example here, phi of Z being greater than 1.6. Well, this is just going to equal 1 minus the probability that Z is less than 1.6. Doesn't matter that I put an equal sign or no equal sign. No. And then obviously we know that that's just phi of 1.6. This next one, I think we have a rule for this. Where are our rules? Here. If Z is between two Z values, you take 5, the bigger one, minus 5, the little one. So let's use that for this one here. This is going to equal phi of 1.5 minus phi of 1 negative 1.2. Okay, we still have this negative Z value, which we cannot work with. So we're going to replace that with 1 minus phi of 1.2. Okay. And this becomes phi of 1.5 plus phi of 1.2 for the thingy there, minus 1. I guess maybe try and graph that yourself and realize why this region is the same as what this one stipulates. That'd be something interesting. Okay, and let's do this last one. So this is going to equal 5 minus 1.3 minus phi of minus 2.5. Now find this is 1 minus phi of 1.3 minus 1 minus phi of 2.5. Expanding this, we get 1 minus minus, those ones cancel. And then it seems like we get phi of 2.5 minus phi of 1.3. Also, do a bit of a sketch and try and think about why that might work. Okay, yeah, that's definitely kind of required of you all because this is kind of interesting and it's also easy to see why this works. Perfect. Now, let's just chuck in this random question and I want you to have a go. So an experiment is run 1,000 times. Its random variable is the standard normal variable, Z. Answer these questions using the empirical rule only. How many scores greater than 2 would you expect? So your empirical rules give you percentages or they give you proportions. Okay. Well, now that you know there's 1,000 trials, you're just going to take the percentage of the 1,000, okay, or the proportion of those 1,000. And then find B if you would expect about 840 scores. Or find B if you were to, I can't even read, if we expect about 840 scores greater than B. Okay, so have a go and then I'll go through the answers now. It says find the number of scores greater than 2. So we want to first find the proportion or the probability that the scores are greater than 2. Doesn't really matter that I put that. Obviously, this is the same as, these are our empirical rules. So we can just go to here, do our little thingy, put in 2, and put in minus 2. I know 95% lies here. And if 95% lies there, then we got to look into the other bounds. So that the outer edges. So this here has to be 2.5%, doesn't it? Because it's 100 minus 95, but then you got to divide it by 2 because it's that and that. Perfect. So this is just going to equal 2.5%. And then it's the proportion of the 1,000. And then this is 25. Perfect. And then find B if you would expect 840 scores greater than B. So the probability that Z is greater than B should equal, wouldn't it be 840 over 1,000? Like that same proportion? The answer should be yes. Perfect. Now that is what, 84%. Lovely, lovely, lovely. Now, where could the 84% come from, knowing our 3 empirical rules? Well, clearly, okay, B has to be somewhere to the left. Why? Because it's saying the probability that you're greater than Z has to be 84%, which means that has to be more than the 50%. Okay. So if this is 50%, it means that this here, let's put it in red, from here to here, should be 34%. Oh my gosh, doesn't that 34% remind us of one of them? Yeah, it reminds us of -1 and 1. So it means B has to equal -1. And you can confirm that for yourself if you worked backwards, like you did what we sort of did in part A. Perfect. Now you can also get asked these sort of scuffed questions. I don't like them as much, but here we are. Find the 9th decile of the standard normal distribution. Find the 3rd quartile and find the first quartile, and then use the interquartile criterion. What proportion of the scores of a standard normal variable would be expected to be outliers? Okay, so what does decile mean? Well, your ninth, first of all, decile means like a tenth. Okay, so like 10%, 20%, 30%. So the 99th percentile is the 90th percent. Okay, hold on. The ninth decile is the same as the 90th percentile. That's kind of like ATARs, right? If you get a 90 ATAR, it means you're in the 90th percentile. That doesn't mean that you're in the top 90%. No, it means that you did better than 90%, which means you're in the top 10%. Okay. So we got to find the particular score. So the probability seems like that Z is less than, we can call this, X, some particular value, has to equal 0.9 because it means 90% of people did worse than you. Okay. Wonderful. So now, like, how do I do this? So obviously we can't really use our empirical rules. Seems like we have to say, well, okay, that means like phi of what X value is going to equal 0.9. So let's go to our trusty table. You could look at the numbers close to 0.9. You see this? 0.899973, 0.90147. So actually, yeah, this is important. So if we take these two numbers, 0.89973 and 0.90147, and we consider where they're coming from, they're both coming from 1.2, and particularly they're coming from 1.28 and 1.29. Okay. Interesting stuff. So now you're going to say, well, okay, well, clearly it's somewhere in between, isn't it? Right? It's got to be somewhere between the 1.28 and the 1.29. Now, you can't just take the middle of it, even though most likely it'll be the middle. So you have to sort of do some extra interesting work. You'll see. So I have those two numbers, and it's 1.28, 1.29. Paste this. Now that number here is 1.2 for the 5 1.28. And this is for the 5 1.29. Now, even though Z scores don't work with the proportions or the percentages or the probabilities linearly, because we're dealing with it on such a small difference, we're going from 1.28 to 1.29, so we're going to the third decimal place, we can almost assume that it's going to be linear. So we're trying to say, well, if we put a little bit of a diagram, this is where people sort of find it confusing. So please focus. If you have a 1.28 here, and then your 1.29 here, and you know at 1.28, you're at 0.88973. So you're there. And then at 1.29, you're at 0.90147. Then instead of thinking about this as a curve, just think about this as being straight. Okay. Think about this as being straight, and it takes you from there to there. Now, obviously, 0.9 is somewhere in between, isn't it? Like 0.90000. Exactly. Well, what's the difference in the y values? We can find that out. Where's my calculator? Bro, where's my, oh, it's right. Okay. 0.90147 minus 0.88973. Well, 89973, my bad. 0.0147 minus 3.8. Okay, so the difference between these is 0.00174. Wonderful. Well, how much do we actually want to go up? If we start at 1.8, we only want to go up part of the way. So what we can do is, because we assume this is linear, we can set up a bit of a ratio. Okay, we can say, well, if I move all the way to the right and then all the way up, that gives me one expression for the gradient of this straight line. Okay, so you can say the gradient would equal, and let's do rise over run, so 0.00174 over, and then what's the difference? 0.01. Wonderful. But we can also get another expression. We can say, well, what if I only go up enough such that I've made it to 0.9? How much do I have to go across in that case? Okay. Now they should give us the same expression for the gradient, obviously, because it's a straight line. Doesn't matter whether you take rise over run from these 2 points or 2 other points, doesn't matter. Okay. Well, what's the rise for this one? The rise for the green is going to be 0.9 minus the 0.89973, which is 0.00027. Yeah. Yes. So then this is going to equal 0.00027 over, and it's going to be some movement in the x. So we can call this t. Sure. Now, because these two gradients equal each other, we can equate these two, and we can just solve for t. So cross multiplying, dividing by that, we can just find this out really quickly. 0.00027 times 0.01 divided by 0.00174. Okay, so we get t equals 0.00155172413. Okay. Now that there is just how much we moved from 1.28. So I just got to add that to the 1.28. So therefore our x, which is our z score, is going to be 1.28 plus that t value. Okay, so it's going to be 1.28155172. And depending on what the question might ask, might say to the nearest, 3 decimal places, 4 decimal places, we can just give that for ourselves now. So 1.281 and then 6. Okay. So that's how you do these sorts of questions. You do a little bit of a triangle, find 2 expressions for the rise and run. And the idea is that you're just equating 2 different fractions because they share the same ratio. Okay. And that way you can find how much you move to the right, and then you can find what that x score would be, what that z score would be. I know I chose x, but that's just me choosing some variable other than z. But yeah. Okay. Part B, we're not going to be using that table there. I think that table causes a bit too many confusions. So we're going to use one that's only going to 1 decimal place. So let me just attach this in. Okay, so this one only goes to 1 decimal place. Now part B said find the quartile 3 and find the first quartile of 5z. Now quartile 1 actually refers to, we can say phi of z1 equaling 0.25. Because if you remember, the quartiles split up your distribution into 25%. Okay, so Q1 means after the first 25%. Q2, or the median, means after the first 50%, so the 225s. Q3 means after the first 75%. And then obviously Q4 is kind of like We didn't even have a Q4. Q4 and then Q0, you could say just like your minimum and your maximum. Okay, wonderful. So we want to find 5Z1 equaling 0.25. So we go to this, we say, is there a number here that gives us 5 some number equaling 0.25? No. Now, can anyone suggest why that might not be the case? I feel like that's a rhetorical question. You cannot respond. Well, if you're trying to take the cumulative and it equals 0.25, can it have a positive z-score? Like if all of these z-scores in our z-tables are positive, it means we've definitely passed the middle. And if we've definitely passed the middle, we've definitely passed 50%. Okay. So you can see a bit of an issue here, can't you? Because we can't actually calculate this one. We can't find it by looking at this table. So instead, let's find quartile 3. Okay, I think that'll be a bit easier. And then we can find another way to get quartile 1. So Z of 3 should equal 0.75. That makes sense because it's after the first 75% of scores. So is there a number here that is close to 75? It seems like these two, 0.6 and 0.7. So let me just copy these in. Yeah, and this is like 0 point, and then one of those ones. Cool. Well, obviously it's going to be somewhere in the middle, doesn't it? I cannot really just say 0.65. Okay, that's kind of sus. So let's do a little bit of our graph again. We say these are our z-scores. We have 0.6 and we have 0.7. And at 0.6, we have a percentage of 0.7257. And then we have here 0.7580. Now we're looking for a z-score that has probability 0.75. So somewhere there. Perfect. If we just put these 2 points here and draw in the line, we can find 2 expressions for the gradient. First of all, what's going to be the rise of the entire thing? It's going to be 0.7580 minus 0.7257. Zero 0.0323, and then the rise, and the run rather, is just 0.1, isn't it? Perfect. So that's one expression for the gradient, 0.0323 over 0.1. Perfect. Now another expression is to only have a rise equivalent to going from 0.7257 up to the 0.75. Why isn't that coming out nice? Sort of like that. Now we've got to find this one here. Perfect. So what's going to be the rise in this? It's going to be 0.75 minus the 0.7257. That's 0.0243. I've said 0 way too many times here. And then the run is going to be, we can call it T or whatever. So 0.0243 over T. Now rearranging, we can find T. 0.0323. Perfect. And that means our z-score for Z3, which should correspond to that point there, is 0.6 plus that. So 0.6 plus T which we can say is 0.6752. Wonderful. So we've approximated what that percentage is. Okay, lovely. Well, if you find Q1, if you find Q3, on a little bit of our diagram, let's take this sort of here. Let's make it a bit bigger. Okay. What we found is we found some Q3 here such that all of this percentage is 75%. Doesn't that mean that this percentage here is 25%? So just the complement? Perfect. So now if you chuck in negative Q3 here, shouldn't that also be 25%? Because that's going to be symmetrical to this. And it turns out that because the median is 0 and our sketch is symmetrical, or our curve is symmetrical, Q1 just actually equals the negative of 0.6752. So there you go. You found Q3 and you found Q1. Wonderful. Perfect. Now, part C. Use the interquartile range. What proportion of the scores of a standard normal variable would be expected to be outliers? Now, what's your definition for outliers? Okay, I think it says, so outlier. Now, I don't know how your reference sheet has it, but I'll write it in a different form. You know you have an outlier if your score, in this case Z, okay, is greater than Q3 plus 1.5 times your interquartile range, or if Z is less than Q1 minus your 1.5 times interquartile range. Okay, so all you got to do, what proportion of the scores? Well, you would just have to chuck those in. Proportion of scores, the outliers. Okay, you chuck those scores in. Actually, it's worth doing, isn't it? So this Z is going to be greater than 0.6. What do we write? 0.6752 plus 1.5 times, and then our interquartile range is Q3 minus Q1, which is just twice of Q3 in this case. So 2 times 0.6752, 2.7008, and then negative, and then this is just the negative. So okay. So what you're saying is you want to find the proportion, so the probabilities. What's the probability of the percentage of scores that are greater than 2.7008? And we can put here or Z less than minus 2.700. Which means on your sketch, you look like this. You kind of want to find these areas here. Perfect. So you can just go to your Z-score table and figure this out. Particularly because they're the same area, it can just do with one of them and then double it. So Z being greater than 2.7008 is equal to 1 minus probability that Z is less than 2.7000. Yeah. And then this is 1 minus, and then if we go to this, I mean, either way, whichever triangle, whichever table we use, we're going to be rounding. So it's 2.7, 0.9965. So 1 minus 0.9965 equals 0.0035. And then your final proportion equals twice that, so 0.007. Okay, because that's the same as that. Perfect. So you may ask, well, how useful is the standard normal distribution if we don't always have a mean of 0, and our standard deviation isn't always 1, right? Like I did mention at the beginning, that marks in an exam is a prime example of a normally distributed data set. But for marks in an exam, your mean is not really 0. I mean, you'd hope it's not 0. And we also don't have such a consistent standard deviation of 1. Okay. And also, if this sort of graph here, your standard normal distribution, represented your marks, would also assume that 50% of people got below 0, which doesn't really make much sense. So, I mean, maybe your class did that bad, but whatever. In reality, we have these general normal distributions, which are actually just transformations of our standard normal distribution, which better fit our data set. Okay. So particularly in this case, let's say your marks in the exam is given by this normal distribution. And it has a mean /mode/median of 70. Really, all I did to get this graph is I kind of just took this and I copied it. So the variance for this still equals 1. Okay, and that transformation is quite easy, isn't it? That's simply just me taking x and then subtracting from it the 70 in my equation, the e to the minus a half of this over square root of 2 pi. Okay, because we know just from normal functions and transformations of functions, that shifts it to the right by 70 units. Perfect. But in reality, our variance isn't 1, or most likely isn't 1 for our data set. Well, how do we account for variance? Because we know variance is a measure of spread, so it tells us how close / how far apart our marks are, or our points are, a higher variance means your marks are further out. So what you can see in this example here in red, I don't know if you can hear someone mowing the lawn. That's very annoying. Okay. Well, if your variance was higher, you might get a curve looking like this. Okay. Because it just means that it's more inconsistent. So the values are more spread apart. So here you can say the variance of whatever is greater than 1. Perfect. So now I've written here that we have this general normal distribution. That's a normal distribution that doesn't have a mean of 0 and a standard deviation or a variance of 1. It's got a mean of mu, something that we don't know, but we're writing it generally, and has a variance of sigma squared. Perfect. We can write the PDF of this, whatever it's called, general normal distribution, by sort of dealing with our transformations. You know how we do those shift to the right, we replace the x with x minus mu, and then we dilate it by a factor of the sigma. So we can divide it by the x by the sigma. Anyway, that's how we sort of get to this. And not really necessary for you to know, but it's there. And then you have this 5x, capital 5x rather, which tells us the cumulative. Perfect. The issue with our general normal distributions is that you can have so effectively infinite different normal distributions now. Whereas the standard was just this one that had to fit these two conditions, and it was always going to look the same. And it was really easy for our standard normal distribution because we had these z-scores. But are you going to sit there and find x-scores for all of your new for all of your new normal distributions? You can't, because each of them are going to have different means and different standard deviations. And therefore, each of their tables, these tables that we worked with, won't make sense anymore. Okay. Yeah, I'm not going to create an X table for my particular normal distribution. There's infinite. So what we have to do now is take these general normal distributions, instead of dealing with whatever the mean is and whatever the standard deviation is, saying, what if I sort of untranslate it and undilate it, and I shift it back, or I standardize it? Okay, so if I have a mean of mu and a standard deviation of sigma, how do I change this back so I can take these x scores and make them z scores? Okay. Now, how to standardize your normal distribution? You basically have to use this x minus mu and sigma. You say, well, all right, standardizing A normal distribution just means you take the x values, you subtract the mean of your normal distribution from it, and you divide it by sigma. And what you're left with is a z-score. This is very good, actually. Basically, you can just now standardize each of these random normal distributions that you have. And then you can go back and use your z-score tables. You can go back and use your empirical rule formulas or your empirical rule properties or whatever. And it just makes life super easy. Okay. Perfect. So this is your formula. It's given on your reference sheet. Now, sometimes it can also be written in a different form where it's given by mu plus sigma z. This is just a rearranging of this. Sometimes they ask you for the x score given these three, or sometimes they ask for the z score given these three. Whatever. I mean, you can transform these two formulas anyway. So let's do this easy example here. It says a data set has mean x bar and standard deviation s 3.6. Answer these questions corrected 2 decimal places. What scores would be 1, 2, and 3 standard deviations from the mean? Perfect. Well, in this case, they're asking us for x scores, aren't they? Because we know this 1, 2, 3 standard deviations from the mean business is this whole z-score stuff. Now, if you're 1 standard deviation from the mean, that means your z is plus or minus 1. If you're 2 standard deviations from the mean, that means your z is plus or minus 2. And if you're 3, you're plus or minus 3. Perfect. So you can say z equals 1. What's the x score going to be? It's going to be our mean, which is 12 plus 3.6 times 1. So 15.6. And you can also do z equals minus 1. And this is just sort of, I mean, you can see I'm just sort of applying these rules, right? Do I have to do these ones? No, just sub in the different z, sub in the different sigmas and the different x bars, and you can find them. And then part B says how many standard deviations from the mean are scores 24, 11, and 7.7. Okay, 24, 11, and 7.7. So now these are scores for this general normal distribution. Okay, we need to find the z scores. So z is going to equal 24 minus our mean of 12 divided by 3.6. So that's 12 on 3.6, which I probably should be able to calculate this, but 3.323. Okay. And then you can do the same for the others, like 11 minus 12 on 3.6, and then z equals 7.7 minus 12 on 3.6. Perfect. So that's just getting you used to being able to apply those rules, apply those formulas. Now, what if we had an actual question that asked us for probabilities or proportions? Okay. It said a normally distributed random variable x has a mean of 100 and standard deviation 20. As soon as it says normally distributed, that means we can then go and standardize it, okay? And we can find all of our rules from the z-score tables / from our empirical formulas. So it says write down the 2 conversion formulae between z-scores and values of x. Okay, A, z equals x minus mu on sigma. And then the other one, x equals mu plus sigma z. It says find the probability that x is less than or equal to 110. What we can do is take this 110 and standardize it. So instead of thinking about x being less than or equal to 110, think of it as z being less than or equal to 110 minus your mu over the sigma. Now we know what mu is. Mu is 100, sigma is 20. So this is the same as taking the probability that z is less than or equal to uh, 10 on 20, so 0.5. Okay, very cool, right? Because now we can just find this from our z-score table, which one should we go to? Let's just go to the easy one. Z being less than or equal to 0 0.5, 0 0.6915. Okay, perfect. And here, part 2 says, find the probability that x is greater than or equal to 90. You can say, well, if x is greater than or equal to 90, what if we go and standardize this? If we standardize it, this is going to be the same. I'll write it actually in red. Probability that z is greater than or equal to 90 minus 100 over 20, which is probability that z is greater than or equal to negative 0.5. Okay. Now, actually, this should give you the same number, but you can show that for yourself. Perfect. Now, part C says find the nearest whole number, the value of A. Find the value of A such that probability of x being less than or equal to A is equal to 0.98. So we want probability of x being less than or equal to A to equal 0.98. That's the same if we go and standardize this, the probability that z is less than or equal to A minus 100 over over what is it, 20? Yep, to equal the 0.98. Now, let's just treat this as a z-score. Phi of which z is going to equal 0.98. Okay. So if we come back to this diagram here, where is this? Let me just copy this down so we don't have to keep scrolling back up. We need 0.98 as the percentage. Can I see it here? No, earlier. 0.977, 0.98. These two. Perfect. Oh, so we got to do that rubbish again. I hate this interpolation stuff. So we have 2.0, we have 2.1, and here we have whatever this number is, 0.9772, and then we have up there 9821. Perfect. Let's just connect these dots. Difference between these two. Okay, so I think for the big triangle, we have the rise. We also have the run. The run's just 0.1. Perfect. So 0.0049 over 0.1 equals, and we wanted to get it to equal exactly 0.98. So let's just put this in pink. That means the rise okay, let's just fix this up. There we go. You can find the rise from here. So 0.98 minus 0.9772, 0.0028. And we just need to find this t. Perfect. 0.0028 over t, and we can find t. Okay, so let's just say 0.05714. Okay. And therefore the Z score is going to be 2 plus T, so 2.05714. Okay, wonderful. And now it's saying, well, 5, what number is going to equal 0.98? So we found phi of this Z gives you, oh, sorry, with this Z, 5, this number gives you 0.98. So that means A minus 100 on 20 should equal that Z score. And then just timesing by 20 and adding 100, we get 20 times 2.05714 plus 100. A equals 141.1428. And I think it said to the nearest whole number. So 141. Perfect. Lovely, lovely, lovely. And now I'll give you one more question just to have a go on your own. This is sort of like an applications of this. Have a read, have a go. And yes, now I shall go through. So the Happy Time Chocolate Company manufactures a 100-gram chocolate nougat bar. As with any manufacturing process, these chocolate bars do not all have precisely the same weight, and these bars are known to be normally distributed with standard deviation 2 grams. Yeah. To reduce the number of complaints, the company has adjusted its machinery so that the mean is 102 grams. Such an adjustment does not affect the standard deviation. Okay. Wait, what? Why would they do this? Yep. Use the empirical rule where possible and tables or technology otherwise. Find the percentage of chocolate bars of weight less than stated weight of 100 grams. Okay. So what is this sort of asking? I feel like we can do this. So part A, probability that the X, I'm not using Z because we're not standardized yet, okay, is less than 100. Now, that's the same if we standardize it to say the probability that Z is less than 100 minus 102, the mean, over the standard deviation of 2. So that's the probability that Z is less than minus 1. Now, by just using your empirical rules, slash doing a little bit of a diagram, I think you can see that between 1 and minus 1, that's 68%, which means here and here should in total give you 32%, which means each one should give you 16%. Perfect. And it says part 2 of weight greater than 105 grams. So that's the probability that X is greater than 105. And then of course we need to standardize this. So this is Z is greater than 105 minus 102 over 2. Watch this not be a nice number. Is this a 1.5? Bruh. Z greater than 1.5. Now remember, that's the same as taking 1 minus phi of 1.5. So let's just go find the 1.5 on here. 1.5, 0.9332. Minus 0.9332. This is some number. There you go. That's that percent. Perfect. And then what would be the mean weight needed for there to be less than 1 chocolate bar in 1,000 under 100 grams? This is sort of asking, wait, you should probably read the question. What would the mean weight need to be for there to be less than 1 chocolate bar in 1,000 under 100 grams? So it's sort of like you're asking us, what's the probability if I let the probability of x being less than 100 be one chocolate bar in 1,000, so 1 in 1,000, which of course equals 0.1%, then what must the mean be when I try and standardize this? That is, when I move this and say probability that z is less than 100 minus the mean, I should say 100 minus mu over our standard deviation of 2. And this should somehow equal 0.001. So I guess we've got to go to our table here. You might go, wait, 0.001, I'm not going to find that on here. Yeah, you're right. The reason why you're not going to find that on here is because all of these are positive z-scores. Whereas if you want phi of some z to be equal to 0.001, it's got to be a negative number, doesn't it? Okay. Perfect. So what you want to do is you want to say, well, instead of thinking about this and me finding this z-score such that that's 0.1%, why don't I take phi of z equaling 0. And this is 999. Okay. Because that's going to give me some z here. And that's going to tell me that all of this is 0.999, which means that's 0.001 there, in this little region here. That 0.001 is the same as this 0.001. So whatever this z-score is, just take the negative, and this should give you that cumulative there. Perfect. So if we come back to our triangle, back to our table rather, 0.999. Oh no. Okay, it's going to be between 2.9. Oh no, actually, here we are, 3.1, 9990. Thank God, we don't have to do that interpolation stuff. So that means this z equals 3.1 for this, which means when we come back to this question here, we can say, if you take phi of negative 3.1, that's going to give you 0.001. And therefore, when we standardize this, we actually want 100 minus the mu on 2 to equal negative 3.1. Now, rearranging this, we get 100 minus mu equals minus 6.2. And then this is 106.2 equals mu. So that should be the mean that you want. Perfect. I hope this sort of made sense. This really explains the scope of the normal distribution. Okay. All right, I'm glad this is over.